Hello, I am Taylor Brown, and this is the P stage for exercise 1 of lab 6. We have the schematic here, and then in Multisim, right now we're testing incrementally. So first we're just testing the P stage that's shown right here. So we've used our LM chip. We've used one section of the LM chip to construct the P stage. And these two resistors right here are both 100 kiloohms, but they're in parallel. So they have an equivalence of 50 kiloohms. And then our Rn is 10 kiloohms right here. So our gain should be about 5. I'm using our function generator to supply a positive and a negative 9 volts to the LM chip. And then I'm using this function generator to generate a square wave with an amplitude of 100 millivolts. Here on our oscilloscope, we're measuring our input versus our output. And we can see at the bottom that the input is 128 millivolts, while the output is 632 millivolts. So when we use our gain formula, we find that we have a gain of 4.846, which is pretty close to our desired gain of 5. Okay, now we have just added our integral portion of our circuit to the proportional portion. And when I simulated the integral by itself, it was just a decreasing triangle wave over time. And so when we add that to the proportional stage, which is just a stable gain of 5, we get a triangle wave. As you can see, it just decreased alongside our input square wave. And here we have constructed the integral on our second portion of our LM chip at the bottom right here. So far we have proportional and integral, and then we will add derivative and the summing stage. All right, now we have finished constructing the entire circuit. We have just added onto our previous proportional and integral circuit. We've added the derivative part, and then we also added the summation inverting amplifier right here. And so in our simulation, we see that the input and the output are very similar. They're both square waves, but the output is amplitude or has a gain of about 5. So when the input amplitude is 100, the output should be about like 508. So we have completed the whole PID controller circuit right here. As a reminder, the top left is the proportional, bottom left is the integral, bottom right is the derivative, and the top right is the summation inverting amplifier. So we've constructed everything right here. We're still using the same DC power supply and function generator. And on our oscilloscope, we're getting an expected behavior from our circuit. As we can see, both are square waves, and when the input is 100 millivolts, the output is 488 millivolts, which is pretty close to 500 millivolts.
My name's Carter Hurst, 113-605-311. We got the 5.5 timer with the motor attached. I'm going to show you the first 50% potentiometer. You can show it, I'll show it right here, and then you'll see the speed. Here's a piece of cardboard that I have to show speed. I'm using a 5 volt on my VCC. Turning it off. We're going to go slower. Turning my potentiometer left, lefty-loosey. Turning on power. Let me try again. You hear the sound? That means the potentiometer has lost resistance. And then with the highest, with the least separated, we have the least separation right here. And of course you see the speed. And that's all using a DC power source, using a 5.5 timer to average the power.
Hello, this is Brayden Black. And for exercise 4 of Lab 6, we're asked to deal with noise measurement, RMS, noise, signal-to-noise ratio. And so for the first part, we are asked to use the 3-op amp circuit built from the last lab. And here we're just verifying that it works, and we get our desired output wave when using 100 hertz, 20 millivolt peak-to-peak voltage. And when converted to RMS, this is about 1.4708 volts RMS. And next, we remove the function generator input and we short it, and so now we can measure the noise generated from the entire system. And so, as we can see, we get a small little voltage peak to peak. The value ranges from like 12 to around 40 at some peaks. So average is about 24 pops up a few times, so we get around 24 millivolts peak to peak as the noise generated from the circuit. And so using the values that we got from measuring, we can then calculate the signal-to-noise ratio unfiltered, and that comes out to about 45-ish dB, which is our expected value. And for the next part of the exercise, we now hook up our low-pass filter, which ours uses a 47 nanofarad capacitor and 10 kilo ohm resistor, which equates to around 350-ish hertz cutoff frequency. And so when we then measure with, again, no input from the function generator, we can actually see that we do get a lower output, which it ranges from 8 to about 20 or 30 millivolts peak to peak, which is a bit less than our unfiltered noise. And after some short calculation, we can see here that our voltage, noise, RMS for the filtered is about 5 millivolts less than our unfiltered noise. And for the final part of this lab, we then reattach the voltage input from the function generator, still with the low-pass filter attached, and we can see that we still get the same output, but decreased ever so slightly from the filter to around 4.02 volts peak to peak. And when converted to RMS, we get around 1.4213, which is not a significant decrease. However, when we calculate the new signal-to-noise ratio of the filtered circuit, we get a significant increase to around 52 from 45, which means our filter works very well and takes out a lot of the noise, making our signal more clean.